Hello everyone, my name is Mayur Ubale. I am an assistant professor in Civil Department WIT Solapur. So today we are going to design a rectangular plane sedimentation tank. So what are the learning outcomes? Students will be able to design a rectangular plane sedimentation tank of water treatment plant. So this is the typical diagram of plane sedimentation tank. If you can see, the water is coming through the inlet channel, it is getting collected in the tank and it is transferred from left to right. If you can see, there are two parameters, that is capital H, which is the total height of the tank, and what is a small h, it is the effective height of water, which we can calculate by subtracting the freeboard, that is generally taken as 0.5 meters to the capital H. We can get the small h, that is the total height of water or effective height of water. As the water passes from the left to right, this is the total length, that is capital L, and if you can see in the plan, you can get the breadth, of the tank. Now let us see one problem with the help of which we can understand the design of plane sedimentation tank. So what is the design statement? Design a rectangular plane sedimentation tank for following data. First, required outflow from the sedimentation tank given to be 300 meter cube per hour. Water used in desludging is 2%. Minimum size of particles to be removed is 0.018 mm. Expected removal efficiency of minimum particle size to be 75%. Nature of particles will be discrete and non-flocculating. Specific gravity of particles to be removed will be 2.65. Assumed performance of settling tank is good, that is N we have to take to be 1/4. Kinetic viscosity of water at 20 degrees Celsius is taken to be 1.01 into 10 raised to minus 6 meter square per second. So for the first, we have to determine the average flow rate, that is Q. The sedimentation tank is to be designed, has to be checked against the resuspension of deposited particles. So what does it mean? Well, first we have to check whenever the flow rate is there, whether that flow rate is disturbing the settled particles or not. To do so, the required outflow rate, which is given in the problem statement, was 300 meter cube per hour. So we have to provide additional 2%, that is your water loss, that is our Q, will be 100 divided by 100 minus 2 into 300. So it will become 306 meter square per hour. Now second is computation of settling velocity of minimum size particles. For this we have to assume Stokes law, which must be valid. So what is the formula for Stokes law? Vs is equal to G by 18 in bracket Ss minus 1 into d square by nu. So we know all the values, that is 9.81 divided by 18 multiplied by 2.65, which is given in the problem statement, minus 1 multiplied by 0.018 into 10 raised to minus 3 whole square, that is diameter of particle, divided by kinetic viscosity, which is given in the problem, that is 1.01 into 10 raised to minus 6, which will be coming about the total value to be 2.88 into 10 raised to minus 4 meter per second. Now you have to go for Reynolds number, that Vs multiplied by d by nu. So it will be 2.88 into 10 raised to minus 4, that is your velocity which you had calculated, multiply by 0.018 into 10 raised to minus 3 divided by 1.01 into 10 raised to minus 6, which is coming about 0.00513, which is lesser than 1. Therefore Stokes law is applicable and computations for velocity is done and also it is valid. So Vs we have to take as 2.88 into 10 raised to minus 4 meter per second, as this velocity is valid. Now going for determination of surface overflow rate. So for an ideal tank for 100% removal of minimum particle size, the surface overflow rate will be equal to the settling velocity of minimum size particles. Otherwise, if suppose the velocity, the overflow rate is not equal to the minimum velocity for the minimum size particle, some particles may get settled, some particles may not get settled in the settling tank. Therefore, it must be 100%. Therefore, we assume SOR is equal to Vs, which is always equal to 2.88 into 10 raised to minus 4 meter per second. Now, we have to convert meter per second to meter per day. So, what we have to do? We have to multiply it by 3600 multiplied by 24, that is in hours you are converting, then you are converting to what we can say days. So, you will be getting 24.88 meter per day. However, due to some kind of a short circuiting, like sometimes due to heavy wind, the velocity may increase or may decrease. Some abrupt changes may happen, due to which the short circuiting can take place. So, we have to assume that condition too. So, due to short circuiting, there will be decrease in the efficiency, due to which SOR may get reduced. So, we have to use the formula, that is Y by Y naught is equal to 1 minus in bracket 1 plus NVS divided by Q by A whole bracket complete raised to minus 1 by N. Here Y by Y naught is given to be 0.75, that is 75% efficiency is there, and it is having a good performance, which is told in the numerical problem. So, you have to take N is equal to 1 by 4. So, by putting these values in the equation, what we will be getting? Vs divided by Q by A, which is equal to 1 by N, total bracket again in bracket 1 minus Y by Y naught raised to minus N minus 1 whole bracket complete. Just by calculating, what we will be getting? Vs by Q by A is equal to 4 in bracket, again in bracket 1 minus 0.75 raised to minus 1 by 4 minus 1, which is coming to be 1.657. So, what is our design SOR? It is basically Q by A. So, which is also equal to Vs divided by 1.657. So, automatically we know the value of Vs. So, just put it, that is 24.88 divided by 1.657, which is equivalent to 15.02 meter per day. Therefore, the normal velocities of SOR generally kept between 15 to 30 meter cube per meter square per day for plain sedimentation tank. As it is coming in between the range, so our design SOR, that is design surface overflow rate, is correct. Coming to the fourth step, that is determination of dimensions of tank. We know the SOR, so SOR is Q by A. Just by rearranging, we can get the surface area of tank, that is A is equal to Q by SOR. We know the value of Q, that is 306 meter cube per hour, which we had found out in step 1. Multiply by 24, because we have to convert meter cube per hour to day. So, we are multiplying it by 24. So, you will be getting the values in meter cube per day, divided by SOR, which we had found out in earlier step, that is 15.02 meter per day. So, you will be getting the value to be 488.9 meter square. Now, you know the area. Now, let us assume length to breadth ratio, that is L to B ratio to be 4. We can take between 3 to 5. So, just putting the values in the equation, that is L into B, which is our area, it means L into B is equal to 488.9 meter square. As we had assumed L to B ratio is 4, so L become 4B. So, 4B multiplied by B is equal to 488.9 meter square. So, B will become in the root 488.9 divided by 4. So, you will be getting 11.1 meter. As we know the breadth, we can easily calculate the length, that is 11.1 multiplied by 4, which is 44.4 meter. We know the length, we know the breadth. What is remaining? Height. Now, let us assume the detention time to be 4 hours. You can take between 4 to 8 hours. The water depth of a settling zone is generally considered to be Q into T naught divided by A, where T naught is our detention time. So, we know the Q, you know the area also. So, just put it in the equation, that is 306 meter cube per hour multiplied by 4 hours divided by 11.1 into 44.4, which we had calculated earlier. So, we are getting the value up to 2.48 meter, as the water depth, that is small h, is always between 2 to 4.5 meters, as it is coming within the range, so it is right. So let us check all the design with respect to score. That is our step 5, that is Vd is equal to, in the root, 8 beta g divided by f in bracket ss minus 1 into d. By taking beta is equal to 0.04 for unigranular sand, because in the sedimentation tank we assume that the particles which are coming will be unigranular. By taking so, beta will be 0.04, f is 0.03 for settling tank, so f will remain the same. So Vd will become, in the root, 8 into 0.04 divided by 0.03 multiplied by 9.81 in bracket 2.65, that is SS, which is given to us, minus 1 into 0.018 into 10 raised to minus 3, that is also given in the problem. So Vd will be 5.57 into 10 raised to minus 2 meter per second. As the horizontal displacement velocity is given by Vh, which is equal to Q by B into H. As we know the Q, that is 306 divided by 3600, because you are converting into seconds, hours to seconds, that is why we are dividing it, divided by 11.1 into 2.48, which will be coming about 3.09 into 10 raised to minus 3 meter per second. As the horizontal velocity is smaller than the Vd, therefore our whole design is correct. It means that the horizontal velocity is lesser than the velocity of settling of particle. So all the particles will be settled, that is 100% efficiency as per our design will be reaching. So let us have few review questions. First, the depth of rectangular plane sedimentation tank is kept between 2.5 to 5, whether this statement is correct or false. Second, maximum detention time in rectangular plane sedimentation is. Then minimum length to breadth ratio in a rectangular plane sedimentation tank is. So let us have its answers. First, yes, it's a true statement. Design depth of rectangular plane sedimentation tank is always kept between 2.5 to 5 meters. Maximum detention time in rectangular plane sedimentation tank is always kept to be 8 hours. And minimum length to breadth ratio in rectangular plane sedimentation tank is always 3. These are the references I have used to make this presentation. Thank you.